So now if you have the whole section is like this, then you have this is EY1 and this is EY2. Now that would mean if I now take the similar triangles, this is XU from this location up till this location. Your XU, if I take two similar triangles, one is the whole section and other is the half. This half with respect to the whole of this would be XU divided by the total length minus, so that would be divided by, for example, I say D. If I call this whole small d right from here, the center of this till this point, if this is D, small d would be equal to, what is the amount of strain here, ECU on XU side, if I'm taking only this portion of the similar triangles, divided by the whole section, this plus this, that would be 0.0035. And what is the amount of strain on EY is 0.004. Now what is D here? D would be 600 minus 600 is the length of this, minus you have how much, 58 mm, that is 542 mm. Thereby XU would be equal to 0.0035 plus 0.004 is 0.0075 into D is 542, so it's 252.9 mm is your XU. Now where is the center located? Center is located at 300 mm. From this position it would be at 300 mm. Thereby, and we have to determine the design strength. Let me first determine the values of EY1 and EY2 and EY3. How much is the amount of these three? Now EY1 is how much? How much is it? 0.004, which we just determined, this one 0.004, because it's at the extreme fiber पे सबसे ज़्यादा tension होगा develop, so it will be for this. That's why हमने यहाँ पर भी वही implement किया from similar triangles. EY1 की location पर 0.004 लिया. Now correspondingly from this similar triangle, how much is EY2 then? ये triangle would now have, this would be, ये distance कितनी है? Right from here to there, this distance is 252.9, so the rest of the distance is 600 minus 58 minus 252.9, That's 289.1. So this is 289.1 mm, the distance from this point, the center of this, up till the neutral axis. Now EY1 we know is 0.004. Now again from the similar triangle, then your EY2 would be by EY2 by EY1 would be equal to, what is the distance of this EY2 from neutral axis? And if this is at 300, which I just told you, 300 minus 252.9, that would be 47.1. So this is at 47.1. It's 47.1 divided by EY1 is at a distance of 289.1. Thereby EY2 is into EY1 is 0.004. 6.5 into 10 raised to 6.5 into 10 raised to minus 4. That is 0.65. 1, 2, 3, 4. Yes. So this is the strain in EY2 0.00065, which will be obviously lesser than EY1 because यहाँ पर loads are lesser. The tension loads here at EY2 position are lesser. Now EY3, now we have to determine EY3, how much is that? Again from similar triangles. Now this is located at a distance of, now XU you know it's 252.9. This is 252.9. Now this point EY3 is located at a distance of 252.9 minus 252.9 minus, you have 58, that's 194.9. It's at 194.9 mm. So your EY3 divided by ECU would be equal to 194.9 divided by 252.9. Thereby EY3 is equal to 194.9 divided by 252.9. That's into ECU is 0.0035, 0.0027 is the strain in EY3. So we have got the values of EY1, EY2 is 0.00065 and EY3 is 0.0027. So these are the values of the strain. Next you calculate the design stresses now corresponding to all these strains. Now we have the stress envelope here. This is the stress envelope. Now corresponding to these, how do we calculate the stresses for steel bars? Yes, any one of you? How do we calculate? You take the graph from IS456 as we took earlier in page number 70 of IS456. Now, what are the stresses? One is EY1 is 0.004. The strains, this is 0.004 right here, and corresponding to the design curve, the stress would be this much. So this is just above 0.85, so around 0.855 or 0.86. So thereby FS1 would be FS1 corresponding to EY1 would be 0.86 FY, or you can just maintain it at 0.85 FY, the maximum one. Then the second one is EY2, which is 0.000. There are 3 zeros, not 4 here. This is point. Three zeros here, 0.00065. You would have 0.0065 would be, this is 0.001, 0.00065, 0.0003 is here, so 0.0007 is here, so it's somewhere here. Now this curve is touching, this point is touching the curve here, somewhere here, or below this, just below this here. If this is 0.8, let me count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19, 20, 21, 22, 23, 27, 27.8. Now this is at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you have 0.8 divided by 27 into 13. This is around 0.38. What we are getting is the stress at EY corresponding to EY2, which is FS2, is 0.38 FY, or then you have corresponding to this FS3, which would be corresponding to C2 compression force for strain EY3, which is 0.0027. So 0.0027 is somewhere, this is 0.002, then 0.003 is here, so 0.0027 is here. So this corresponds to 0.8 5 and 0.8 के बीच में, that's 0.84 around, this is 0.84. FS3 corresponds to 0.84 Fy. Now, having determined the stresses at all these locations, you can now easily determine the, yes, one is left, which is FS3. Sorry, that's done. So FS3 is done. So now there is a difference. Now this is in compression, these are in tension. This is in tension, this is in tension. So we can say this is positive and these would be negative. Then in that case, now we can easily determine the stress or the strength at each of these locations from the design stress strain curve. What is Fy? Fy is 500, so this would be point. How much would this be? 0.85 into 500, that's 425 megapascals. This would be 0.38 plus 1 into 500, that's 190. You can take it by convention in negative as well, this one, or you can keep the negative sign outside like this, negative, negative, like this, not here. And this would be 0.84 into 500, that's 420. Now this is positive. Then in this case, you have, now how much is this? The maximum 420 megapascals is FS3, and on the tension side you have 425 megapascals. So you are getting more on the tension side, that's 425 megapascals is the stress in the steel on the tension side. Thereby the design strength in axial compression would be Yes, any one of you who can guess what will be the design strength? What will be the design strength? It will be a combination of all these forces. It will be combination of summation of C compression forces as well as of concrete and of steel. So we have already discussed that, C1 and C2. And so the design strength in compression would be the combination of these two. Now CC is how much? It's 0.362, as we already know. CC or C1, that is 0.362 FCK into XU into B. This is how we do in the compression. Now we already know 0.3, this is 0.362, this is 30, then your XU is 250, 258, 252.1. 0.9 into your the lesser direction, that is 350B, because you are calculating it about the width of the section, like you had in the columns, in the beams. You would calculate it about this B. This would be XU and this would be B. So it's 350. So this comes to be 0.362 into 30 into 252.9 into 350, 961,272.9 Newton. So that is 961.3 kilonewton is the compression C1 or CC. Then you calculate CS. Now CS is the combination of, now this is when you have actual compression. In compression, you will treat all of these, even the tension ones. We are first assuming that this is the step number one, where we are determining the design strength only in compression under the compressive loads. In that case, all these three will also contribute to compression, but we do not assume any portion of this to act in the compression of the concrete in the tension side to act in the compression. Rest, we assume all the steel to act in compression, where summation of all the compressive forces, that's C1, one is due to FS1, the other is due to FS2 and FS3. Let that be C1, then you have TS1 and TS2, the summation of the forces. Now in compression, when they are all acting in compression, they still would have their signs, because the other portion is in tension. So C1 is contributing to how much? 420 megapascals. Now into what? Into its area. So let me, if I can get the summation sign here. So this would be equal to the summation of CS, all CS, that would be summation of FS in all FS in compression minus all FS in tension into, you have stress into area of steel of each one of these, into area of steel of each one of these. This is into ASC. So you have CS equal to this. Now, whether it's ASC or AST, whatever the designation you put, it is, you can say it's ASI, corresponding to any value of FS1, FS2, or FS3, you can say it's ASI. Then in that case, your, this would be number one, FS corresponding to FS1, it would be 425, but it's minus. Next, you have corresponding to plus again you have minus fs2, that's 190, then corresponding to fs, that's 420. This is plus into, you have what is the area of steel in total. How much did we get the area of steel? 1657.92, and we are calculating for the whole area of steel 1652 point कितना था? 1657.92, 1657.92. So this would be 1657 point, this is minus 425 minus 190, कितना आ रहा है? 323.294. or just 3 kilonewton, and it's in tension, negative sign. So overall, your how much would now be CC plus CS? The design strength would be 961.3 minus whatever is coming in tension, that's 323.3. So the actual force is actually decreasing because there is a tension happening on the other side due to eccentricity. The actual force, the design strength of this section is actually decreasing due to the eccentricity. So it's 638 kilonewton is the design strength in actual compression of this section. So having calculated this, we can also calculate the design strength in flexure. Design strength that was in tension compression. Next in flexure would be this would be the moments, the addition of moments. The total design strength would be MC plus M, whatever the designation, what did we use earlier? We used MC plus MS. This is MU or MUR because it's the moment of resistance that the section can take. Now, MC is the moment of resistance taken by the compression side. That would be, and we already know this equation from the beams. The compression में कितना लेता है? This is CC into, it's 0.447, or you get, if you just assume it to be close, it could be 0.5 or 0.447 minus Oh, this is at the center. This is 0.5 minus 0.416 XU. That comes out to be around, how much is CC? We have calculated CC. That is 961.3, 0.5 minus, this is D. D is at, sorry, this is D. Our D is not 0.5, sorry. This would be, how much is our D? 0.5 point. Our D came to be around 600 minus 58, 542. It's 0.4542. This is D 0.542 minus 0.416 XU. So this is 0.542 minus 0.416 XU is how much? 258.9, 252.9, 252.9. So this is our XU. Then this total would be 961.3 into 10 raised power 3. This is into 961 point, that's 0.416 into 0.2529 minus 0.542, 0.436 into 961.3 into 1000. That's 419889 newtons. That's 419.88 Newton meter. That's kilonewton meter. Your MS similarly would be, it would be the summation of all this summation Fy. What do you have determined? No, not Fy, Ty or CSI. I can write it as CSI into the distance Yi, the lever arm at which it's acting. Now, the lever arm at which it's acting, each one of these is known to us, and the stresses are also known to us. The first one is your Fs1. It's acting at a distance of, from the center, it's acting at a distance of 242 mm. So this is into 242, because now it's on the negative side, so it would be minus 242 on this side of the lever arm, plus you have then Fs2. Your Fs2 is acting at zero distance from the center. plus fs3. Now this is on the compression side, it's acting at 242 again, but this is positive. Your fs1 is given as not fs, this is t1. T1, this would be T2 corresponding, because we're calculating the, we have already calculated the load into lever arm. This is T3 or C2 corresponding to, thereby T1 is known to us. T1 is did we calculate T1 somewhere? Corresponding to lever arm, it will be stress into